Hey, good evening, everyone. Welcome to O-Level Physics lesson. Today is the 20th of September. My name is Mr. Chu, and today we'll be going through the last topic of thermal physics. Okay, the theory of the thermal physics, which is thermal properties of matter. Okay, so that will be what we'll be doing today. Okay, so let me show you how the physics content is structured. Okay, so as you can see over here, we have completed. Okay, we have completed the section 1 and 2. Okay, we are almost completing section 2. And so now today, okay, so we will be doing the last part, all thermal properties of matter. Okay, so how is everyone? So let me. Okay, so what actually exactly is the thermal properties of matter? So let me just briefly go through the topics, the subtopics. Okay, so we need to know about internal energy. Okay, so we have talked about this previously already. We have talked about this previously already. However, let me just repeat myself again. Okay, so for all matter, okay, they always have internal energy. Okay, it's internal energy as an energy store. Okay, so it's internal energy as an energy store that is made up of two things. Okay, it's made up of two things. So let me write down here. Okay, so internal energy of every metal is made up of two things. Okay, first of all, it's made up of the total kinetic energy, okay, which is related to the random motion of the particles. Okay, and this is actually related to the temperature of the metal. Okay, you all remember that? If it moves faster, when the particle moves faster, okay, the particle move faster, you actually have greater kinetic energy, and this kinetic energy is one of the two parts of the internal energy. Okay, the second part of this will be the total potential energy between particles. Okay, so I have talked about internal energy in the first lesson on the particles itself. Okay, give me a moment. Okay. Okay, so basically, the total internal, okay, the kinetic energy relates to the how fast your particles are moving, and that is related to the temperature of your metal itself. And then the potential energy is due to the forces between the particles. Okay, so we have learned that in the chapter on the kinetic particle model. Okay, so do you all need me to explain further on the internal energy? Okay, if you all need me to explain further, give me a yes question. If you are okay with internal energy, give me a thumbs up. Okay, Ray Ho understand internal energy. Sixian and Siren, are you clear about internal energy now? It is something that we have covered in the kinetic model. Siren, are you okay? See, are you there? Okay, the next thing, if have you all learned this in school? Have you all learned this? The next part here, specific heat capacity or heat capacity and specific heat capacity. Have you all learned this in school? Okay, if you learn this in school, give me a yes reaction. If you have not learned this in school, give me a no reaction. Because it will take a bit of time to learn this. Okay, if you learn this in school, give me a yes reaction. If you have not, give me a no reaction. Okay, so Siren, because you're in Sec 2, you're not learning. Okay, then I will explain a little bit faster. Siren, if you don't understand what I'm saying, please let me know. Clear? Okay, so different matter. Okay, the matter talking about this matter. Different matter, different object. Okay, will have different capacity. Okay, for different capacity to store internal energy. Okay, so let me give an example. Liquid water and liquid mercury. Okay, liquid water and liquid mercury will have different capacity to store internal energy. Yes, so far? Okay, so what are the factors that affect this capacity? Okay, it could be number of particles. When you have more particles, you need more thermal energy to raise its temperature. Does it make sense? For example, you are going to shower. Okay, and how many of you likes hot shower? Okay, if you like hot shower, give me a yes reaction. If you like cold shower, give me a no reaction. 都是Ray Hong like cold shower. Okay, you are funny. I'm like serious like hot shower. Okay, so when you prepare hot water to shower, okay, the amount of energy needed to raise the temperature of 1 liter of water versus 10 liter of water, which one will require more energy? 1 or 10? Okay, write it down in the chat. Which amount of water will require more energy to raise the temperature by the same temperature? Okay, so you say 10. Very good. Remember, put down the unit 10 liter. We all say 10. Okay, very good. Okay, so when you have more particles, you are actually able to store more energy, and therefore it will require more thermal energy to raise its temperature. Clear about that? Okay, then different material, in this case, water and mercury, they are built up differently. The bonds between the water and the bond between the mercury molecules are all very different. Am I right to say that? Okay, so the intermolecular forces of different matter will require different amount of energy, okay, to expand and contract, okay, to actually absorb or give out energy. Is that clear? Okay, so let's go to heat capacity. What's the meaning of heat capacity? Okay, let me start. Okay, so heat capacity, let me write down. Oh, no. Let us see. Oh, the new way of this Zoom. Oh, how to change color. Okay, so for heat capacity, so heat capacity of an object is the change of its internal energy per unit change in its temperature. Okay, for a start, this might not seem easy to understand. Okay, so basically, the heat capacity tells you how much energy is needed to increase or decrease its temperature by 1 unit. Okay, so the 1 unit usually is a Kelvin. The SI unit of temperature is Kelvin. Okay, which has the same difference in degrees Celsius. Okay, so I repeat myself again. A heat capacity of an object. Okay, the short form for this is capital. Okay, is the amount of energy required to increase its temperature by 1 unit. Okay, so what's the unit for this? The unit for this, the unit is the energy. Okay, amount of energy. Energy is joule. Okay, amount of energy required to raise its temperature by 1 unit. So 1 unit of temperature is Kelvin. Okay, so the unit for heat capacity is joule per Kelvin. Is that clear? Okay, so if there is more water, the heat capacity will be greater. But it doesn't talk about per unit volume or per unit mass. Okay, so when we talk about heat capacity of an item, we talk about the item. It could be a 5 kilogram water. It could be also a 10 kilogram water. Okay, it doesn't matter what is the mass of the. Okay, it actually matter what is the mass of the matter itself. Okay, so it's the how much energy to raise all the water, regardless is it 5 or 10 kilogram, okay, by 1 Kelvin of temperature. Okay, Siren, this is something new to you today. After explaining this, are you clear? Okay, Shen and Rui Hong, when teacher explained this, are you clear in class? After I define this one more time, is it clearer to you all? Okay, if you understand, give me a yes reaction. You are still confused, give me a no reaction. Okay, very good. Okay, next. Okay, the difference between heat capacity and specific heat capacity is that specific heat capacity is always the same for the specific material. Okay, just like density. Density of water is always the same. Okay, if you are talking about water, liquid water, it's always the same value. Okay, just like density of gold. How do you tell whether what you're holding in your hand is pure gold? Okay, you go and measure its density. So density is always the same for the pure material. Okay, so when you talk about specific heat capacity of a material, it will always be the same. Whereas heat capacity, you're talking about the 1 kg of water or the 10 kg of water, it could be different. But his specific heat capacity of water is always the same. Are you with me? Okay, so what's the definition of this? Okay, so let me write it down here. Okay, so specific heat capacity is the change of its internal energy. Okay, so far everything is the same. We only add a few things. Let me show you what we add. Per unit mass for each unit change in its temperature. You all see what's happening here? Okay, so what's the difference here? The difference between the definition is there's this extra word called per unit mass. Okay? There's this extra definition per unit mass. Okay, so basically it's how much energy you require to raise 1 kg of, let's say, water by 1 Kelvin of temperature. Are you all clear about it? It's the amount of energy to raise 1 kg of the material by 1 degree Celsius temperature. Okay, so because we talk about per unit mass, it is now very specific. It has to be the same value for all the mercury. Okay, it has to be the same value for all the gold. Okay, the same value for all the water. If you're talking about pure water, whether is it in your house or my house, they both have the same specific heat capacity. So they don't need to care about their mass because you need to divide by the mass. Okay, so in this case, what is the unit of a specific heat capacity? Okay, the unit for the specific heat capacity, okay, specific heat capacity, the symbol is small c. Okay, heat capacity is capital C. Specific heat capacity is small c. So what's the unit for specific heat capacity? Okay, the unit will be the number of energy, which is joule, okay, divide by 1 kilogram of the material and 1 Kelvin of the temperature. Okay, so this is a unit for specific heat capacity. Is that clear? Okay, so let me change color. Okay, so specific heat capacity is the amount of energy. Okay, this energy is Q. For each unit of mass is M. To increase the temperature by 1 Kelvin. So this is the capital T. And then we talk about this with a small c. Small c. So can you see, if I were to rearrange the whole formula, small c is the same as the amount of energy. Energy can be used E. Okay, we can also use Q. Divide by M and temperature. Okay? So are you with me here? Specific heat capacity is the amount of energy needed to raise 1 kg of the metal by 1 Kelvin of the temperature. Are you clear about this? Then, if I were to make Q the subject, okay, then I will be able to get M, C, and T. Are you clear about this? If I make Q the subject, CMT comes to the other side. So M is the mass of the object, T is the specific heat capacity of the object, and T is the change in temperature. Okay, so instead of using T, what we like to do, instead of using T, we actually write down change in temperature. In this case, temperature, we use theta. Okay, theta. Okay, so this is a formula that I will need all of you to remember. Okay, I need all you to remember. Q is equal to mc theta. Okay, which is the same as energy transfer is equal to mass times specific capacity times change in temperature. Are you clear about this? This will be Q, this is M, this is C, this is change in theta. Okay, and it all comes from this formula here. The T itself, I use change in theta. Okay, it's the same thing. So are you all with me? Are you okay with this? If you are okay with this, give me a yes reaction. Siren, are you okay? So let me give you some example of value of the specific capacity of certain item. And so let me remove. Okay, so for liquid water, okay, the specific capacity of liquid water is 4,200 joule per kg per Kelvin. You so far? What does this mean? For 1 kg of liquid water, it requires 4,200 joule of energy to raise it by 1 Kelvin or 1 degree Celsius. You so far? Then I'll give you a bit of more. Okay, so next thing, go. Go is Ag. Okay, the specific heat capacity is just 129. So can you imagine? Okay, so go is just 129. So for the same amount of energy, okay, 1 kilogram of water would require 4,200 joule. Whereas gold, if you supply the same 4,200 joule to gold, to 1 kg of gold, it will actually increase by almost 20 over degrees Celsius. Can you see that? Okay, so that's the meaning of the specific heat capacity. And all the gold in the world will have the same specific heat capacity. Are you clear about this? Okay, all the gold in the world will have the same 129 joule per kilogram per Kelvin. Okay, the kilogram is okay, another example will be, let's say we talk about tungsten. Tungsten, you all know what's the short form? W, right? Okay, tungsten, 132 joule per kilogram Kelvin. Okay, brass, 380 joule per kilogram Kelvin. Okay, and so on. Okay, so can you see? among many material in this world, to raise a temperature of water, okay, 4200 K for water, you require quite a bit of energy to raise it by one temperature. Okay, one unit temperature. You see that? Okay, so can you imagine our water itself actually is a very good store of energy. Okay, because when you give it 4,200 joule of energy, it only increased by 1 Kelvin. So can you imagine how much energy is needed to raise or cool the seawater itself? Quite a long time, right? Okay, so are you all clear about this? Okay, let me give an example. Let's see if we can do a simple example. Um, okay, so first we talk about water has a heat capacity of specific heat capacity of 4,200 joule per kilogram Kelvin. Okay, then another example would be steel. Steel has a specific heat capacity of 460 joule per kilogram Kelvin. Okay, so the question now is this. I have 25 gram of steel spoon heated up to 150 degrees Celsius. Okay, and I use 300 gram of tap water at 24 degrees Celsius to cool the steel spoon down. So my question now is, what is the final temperature? Can all of you complete now? What is the final temperature of this? Can you all calculate? Consider your understand the you don't get any answer, if you need help, just say help. Help. You see, you need help. How about the other two of you? Do you need help? Wait, oh, and see, and Shixuan, are you still calculating? Okay, Shixuan, okay. Hold on. Okay, let me explain this to you. Let me open up another. Okay, so basically we have a spoon, put inside water. Okay, so the water is 4 degrees Celsius. The spoon is 150 degrees Celsius. Okay, this is a steel. Okay, so this is 25 gram. Okay, for this case, it's 300 gram. Okay, so the specific heat capacity of this steel is 460 joule per kilogram Kelvin. And then for water, is 4200 joule per kilogram Kelvin. Okay, so on the left, you have 150 degrees Celsius. On the right is 24 degrees Celsius. You put this inside the water itself. Energy from the steel spoon, because it's a higher temperature, will actually go to the energy to the cooler liquid water. Clear so far? Okay, so the temperature of this should drop, the temperature of this should increase to a point where both have the same, both will have the same amount of temperature. Okay, so we let the new temperature be T, the new temperature be T. Okay, so the amount of energy lost by the steel spoon is equal to the energy gained by the water. All clear? Energy lost by the spoon is equal to the energy gained by the water. Then we use the formula mc theta. Okay, they both has to be, okay, Q is equal to mc theta. Am I right? Okay, so the mass of this spoon is 25 over 1000 kg. The specific heat capacity C is 460. Okay, the temperature difference 150 minus T. Right to say that? The temperature different, the final temperature will be 150 minus T. Has to be the same as 300 over 1000, the mass of the water, multiplied by the specific heat capacity of the water, and the T minus 24 degrees Celsius. Okay, so now I want you all to solve this equation, make T the subject, you should be able to get the answer. Okay, you all go and calculate now. So can you do that now? Make T the subject. Okay, Zixuan, can you please do that again? Because your temperature should be the same. Okay, Siren, your spoon is 150, your water is 24. Eventually, these final temperatures will be between 150 to 24. It shouldn't be higher than 150. It shouldn't be lower than 24. Okay, so Siren, count again. Ray Hong, your numerical answer is correct, but your unit is wrong. Okay, Ray Hong, try again. This is calculate again. I already give you the formula. You just solve this formula. Solve for T, you should get the answer. Ray Hong, your unit is wrong. Zixuan, your 2.53 is what? Okay, what is the unit for T? What is the unit for T? Okay, Si Ren, Ray Hong, and Zixuan, well done. Okay, so if you make T the subject, okay, you all should be able to get 25.1 degrees Celsius. Is that clear? So can you see? Even though the spoon is about 126 degrees hotter than the liquid, but because the spoon is smaller mass and it has a smaller specific heat capacity, okay, when you put it into 300 grams, which is about 12 times the mass of the spoon, okay, the overall temperature just go up by 1.1 degree for the water, but for the spoon it went down by 100 over degree, okay, because the spoon has a very low specific heat capacity. Okay, up to here, are you all clear? Okay, all clear? Okay, then we go to the last part of this topic already. Something. Oh, so many things. Okay, so we have finished with specific heat capacity. Okay, so we're going to talk about melting, boiling, and evaporation. Okay, so all of you know that melting and boiling is a thermal process where there is no change in temperature. Okay, so far? Okay, so for example, if I were to melt ice to become liquid, okay, so I supply energy. Okay, I supply energy to this bucket of ice water. So the ice will tend to melt over time. So during this period, the overall things here, both the ice and the water will have a fixed temperature. Okay, so we talk about internal energy. So when you have a fixed temperature, the kinetic energy is fixed. So when you supply the energy to this system, it is the potential energy that increases. So when a solid become a liquid, at that point of time, during the point of melting, okay, the potential energy goes up. The kinetic energy remains the same. Likewise, when you talk about boiling, okay, when you boil something, the kinetic energy remains the same, whereas the potential energy increases. Now, when we talk about the reverse, when we talk about condensation, okay, the kinetic energy also remains the same, but the potential energy decreases. Likewise, when you talk about freezing or solidification, okay, the kinetic energy remains the same, but the potential energy decreases. You are clear about this? Yeah, you are clear? Okay, if you are clear about what I mentioned so far, can you give me a yes reaction? Okay, so during the process of change of state, there is no change in kinetic energy, but there's a change in potential energy. Is that clear? So if you are clear about this, give me a yes reaction. Okay. Then there are 5 differences between boiling and evaporation. In primary school, you learn about 2 differences. Okay, so now in O level, you're going to learn about 5 differences. Okay, so there are 5 main differences between boiling and evaporation. So let me write down. In boiling and evaporation. Okay, so boiling needs a heat source. Okay, you need a heat source like a fire or Bunsen burner. Okay, but for evaporation, you does not need a heat source. Clear so far? Okay, number 2. It takes place throughout the liquid. Okay, when you boil something, it takes place throughout the liquid. Clear so far? Whereas for evaporation, it only takes place at the surface. Clear? Okay, it only takes place at the liquid surface. Okay, so you have learned point number 2 in primary school, correct? Okay, so number 3. Okay, the rate of boiling is faster. So it's a faster process. Okay, whereas evaporation, since evaporation takes place only at the liquid surface, it is a slower process. Okay, this is what you learn in primary school. Happens only at the boiling point. Okay, whereas for evaporation, happens at any temperature below the boiling point. You all remember that? Okay, lastly, your liquid temperature remains constant. Okay, whereas for evaporation, okay, it does not have a heat source. So you need some heat energy from the surrounding for it to vaporize. Okay, so where does the energy come from? It takes the energy from the surrounding. Okay, so the surrounding is the liquid itself, the original liquid. So at the surface of the liquid, As it evaporate, we actually steal the energy from the liquid below. So the liquid below itself, okay, the liquid temperature will tend to drop. Okay, so for evaporation, it is like a cooling effect. As some of the liquid evaporate, the remainder will lose its temperature because the temperature is being the energy is being transferred from the remaining liquid to the evaporating liquid. Okay, so the remaining liquid lose some energy, lose some internal energy, then temperature drop. Is that clear? Okay, so are you able to remember the 5 differences of the boiling evaporation? Okay, I give you time to write down. If you can remember or have you have written down, give me a yes reaction. Then we'll move on. If you're okay, give me a yes reaction. Zishan, you okay? Okay. So we have finished about boiling and evaporation. Okay, so let's talk about latent heat and specific latent heat. Okay, previously we actually discussed about specific heat capacity. That is the amount of energy required to raise 1 kilogram of the metal by 1 degree Celsius or 1 Kelvin. Okay, so what is specific latent heat? Okay, it's the same thing as this, but we use this term to describe the amount of energy required to change the state. Okay, so there's 2 types of specific latent heat. There is a specific latent heat of hold on. Okay, there's a specific latent heat of fusion. Okay, that is used when you are trying to melt or solidify. Okay, there's also a specific latent heat of vaporization. Okay, that is when you're trying to boil or condense. Okay, you try to boil or condense. Okay, so specific latent heat. Okay, specific latent heat of fusion is for melting and solidification. Specific latent heat of vaporization is for boiling and condensation. So what is the specific latent heat? It is the amount of energy required to, in this case, melt or solidify 1 kg of the metal. Is that clear? Okay, so specific latent heat of fusion means the amount of energy transferred to change a substance between a solid and liquid state at a constant temperature. Clear so far? Okay, so the formula will be Q equal to ml. L is your specific latent heat. Okay, same thing. Specific latent heat of vaporization, okay, also the small l, is the amount of energy required to raise, not raise, required to change the state of 1 kg of the metal between liquid and gaseous state. Okay, so far? Okay, so specific latent heat is L. The unit will be joule per kg. Okay, because it's the amount of energy required to change the state of 1 kg of the material. So fusion is between solid and liquid. Vaporization is between liquid and gas. Is that clear? Can. So now we know that this L is energy divided by mass. So if I were to rearrange the formula to make the energy as the subject, you will get Q equal to ml, which is this. Energy equal to mass times specific latent heat. Clear so far? Okay, so energy transfer is Q multiplied by mass times specific latent heat. So this energy transfer is Q, this is mass, and then this is the specific latent heat. Okay, so let me go back to evaporation for a while. Evaporation, there's a few factors. What are the factors that increase evaporation? Okay, so number one, lower pressure, higher evaporation. Okay, lower air pressure. Okay, number two, higher temperature, higher evaporation. Number three, higher wind speed. Okay, higher wind speed. Okay, a higher evaporation. Number four, you also learn in primary school, higher surface area, higher evaporation. Next, we also talk about humidity of the air. The lower the humidity of the air, in less water in the air, right? The higher the evaporation as well. Okay, number six, the lower boiling point of the liquid, the higher the evaporation as well. So these are the 6 factors that will increase evaporation. Okay, a lower air pressure, higher temperature, higher wind speed, higher surface area, lower humidity, and a lower boiling point. Not blood pressure, it's a lower boiling point. Understand so far? Okay, let me maybe show you. Show your hold on for a while. Okay. Okay, so let me revise. Internal energy consists of kinetic and potential. Okay. We talk about specific heat capacity is the amount of thermal energy needed to raise the temperature of a unit mass of substance by 1 Kelvin of temperature. Okay, change in state. I don't need to go through. You all know this very well. Okay, the only thing I did not go through is from solid to gas is called sublimation. And then from gas to solid is called deposition. Okay, so now we're going to talk about will be the heating and cooling curve. Okay, so can you see as the temperature goes up, your internal energy will goes up. Which part of the internal energy? The kinetic energy. Okay, therefore temperature goes up. Then when it starts to melt, the temperature remains constant. The kinetic energy of the material remains the same, but the potential energy starts to increase until all the solid melt, then the temperature goes up again. So that is when the internal energy, the kinetic energy goes up, where the potential energy remains the same. Until you reach the boiling point, where temperature don't goes up anymore, that is when your kinetic energy remains the same, whereas the potential energy of the material increases until all the liquid change state to become gas. Then the potential energy stop increasing and it's the internal energy increasing. So throughout the process from left to right, the internal energy of the substance kept increasing. Is that clear? Then in the cooling curve, from left to right, it is the opposite. So throughout from left to right, the internal energy kept decreasing. Okay? So from left to right, the internal energy kept increasing. Okay, then in the cooling curve, from left to right, the internal energy kept reducing. Okay, so which part is the kinetic energy that increased? Let me show you all. Okay, this part is when the kinetic energy increases. And this part is where the kinetic energy decreases. Is that clear? So this part is where the Ke increase. This part is where the Ke decrease. Then the part where it's flat here. Okay, where it is flat here is where the potential energy increase. In this case, it is where the potential energy increases. Are you clear about this? So are you clear about this topic so far? Okay, so let me just finish up the revision of this notes. I'll give you the notes later today. So melting and boiling is when temperature remains constant, so Ke remains constant. Okay, so you all read this yourself. I mentioned this previously. Okay, so when we talk about latent heat of a specific latent heat of fusion and specific latent heat of vaporization. So for fusion, it is for a change between solid and liquid. Vaporization is a change between liquid and gas. Clear so far? Okay, then we talk about the difference between evaporation and boiling. Okay, the six differences and the factors of rate of evaporation. Okay, up to here, do you have any question? Okay, I already ended the theory of this topic already. Up to here, any question for me? Okay, if no question, my exit question will be like this. Let me write down. Okay, can you give me the formula of specific heat capacity, okay, as well as a specific latent heat? How much you will want to do, and then how well I teach. Okay, our temperature is capital T. Okay, in this example, we use okay, later I'll share with you. A small t is used for T. Okay, so the formula that you all should remember will be Q equal to mc theta and Q equal to ml. Okay, small l. Capital L is latent heat. They use small l. Okay, Rui Hong and Sishan use a small l. So can you all do that again? Okay, Sishan, Rui Hong, how about Siren? What's your answer? Okay, Ray Hong, give me your formula for specific heat capacity as well. Siren, waiting for your answer before I dismiss the class. Okay. Thank you so much. Thank you for doing the practice question. Have a good night. See you on next week. Bye.